Wavestown. I can identify how different wavelengths on the electromagnetic spectrum, such as visible light and radio waves, are used to gain information about components in the universe.
Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere you go. It is odorless and tasteless, yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves, which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's x ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected, and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green, but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared waves. To learn more about the world around us, scientists and engineers have devised ways to enable us to see beyond that sliver of the EM spectrum called visible light. Data from multiple wavelengths help scientists study all kinds of amazing phenomena on Earth, from seasonal change to specific habitats. Everything around us emits, reflects, and absorbs EM radiation differently based on its composition. A graph showing these interactions across a region of the EM spectrum is called a spectral signature. Characteristic patterns, like fingerprints within the spectra, allow astronomers to identify an object's chemical composition and to determine such physical properties as temperature and density. NASA's Spitzer Space Telescope observed the presence of water and organic molecules in a galaxy 3.2 billion light years away. Viewing our sun in multiple wavelengths with the SOHO satellite allows scientists to study and understand sunspots that are associated with solar flares and eruptions harmful to satellites, astronauts, and communications here on Earth. We are constantly learning more about our world and universe by taking advantage of the unique information contained in the different waves across the EM spectrum.
So let's take a few notes. Electromagnetic spectrum contains waves of different wavelengths. Each type of wave is used to gain information about distances and components in the universe. So up here you have your name of your waves, and down below it's showing you the wavelength of those waves. So, for example, if we look at infrared, they are going to be radio waves are going to be the longest, where gamma rays are going to be the shortest. And if you look here, this is ultraviolet coming out, this is your visible light, and then your infrared here. So, again, your gamma rays are going to be your shortest wavelength, where radio waves are the longest. So, which type of wave has the longest wavelength? If we look down below, you can see your wavelength, and your radio waves are representing your longer waves. Which type of wave has a longer wavelength than infrared but shorter than radio waves? So, which type of wave has a longer wavelength than infrared but shorter than radio? So your microwave would be longer than your infrared but shorter than your radio wave. Explore the different wavelengths on the electromagnetic spectrum directions. We're going to use the descriptions of different electromagnetic spectrum waves and match the type of wave to the letter placed in Wavetown on slide 4. So on your next slide, these are labeled A, B, C, D with a letter, and we're going to read this article to match the description. Okay, so let's click on the description page to the right for a larger copy. And I will read through this. We're going to make a copy. And so this copy will be open in a tab that you can go back and forth on. So Wavetown descriptions. The electromagnetic spectrum is used to study space. The energy emitted by space travels through empty space. The energy from the electromagnetic radiation is useful here on Earth. So there are radio waves. This is the same kind of energy that radio stations emit in the air from your boombox to capture and turn into your favorite tunes. But radio waves are also emitted by other things such as TVs, MRI machines, and even starring gases in space. You may not be able to dance to what these objects emit, but you can use to learn what they're made of. Microwaves. Microwaves, actually radio waves with the lowest frequency. They'll cook your popcorn in just a few minutes. They're also used in radars and cell phones. In space, microwaves are used by astronomers to learn about the structure of nearby galaxies, including our own Milky Way. Infrared. These are used in electric stoves, toasters, heat lamps. We often think of this as being the same as heat because it makes our skin feel warm. Plants and people give off infrared. In space, infrared maps the dust between stars detected by thermograms. Visible. Visible waves. Yes, this is the part that our eyes see. Visible radiation is emitted by everything from fireflies to light bulbs to stars, also by fast moving particles hitting other particles. Each wavelength of light has a different color. Ultraviolet. The sun is a source of ultraviolet or UV radiation. UV rays in small amounts cause our skin to produce vitamin D, but too much can cause sunburns and even lead to cancer. Stars and other hot objects in space emit UV radiation. X rays. They can go through your body to allow doctors to use them to look at your bones and your dentist to look at your teeth. Hot gases in the universe also emit X rays. Gamma rays. Radioactive materials and some nuclear reactions can emit gamma rays. Controlled amounts can be used to treat cancer, but too much can also cause cancer. It makes gamma radiation in all kinds of ways. Gamma rays cannot pass through the atmosphere from space. So we're going to use the description page and we're going to write the wave type in the table next to the letter on slide 4. So here we go. So here, this is your activity. So we're going to look at the letters in Wavetown. So letter A, what type of wave? It's going to be a visible wavelength, and placed used in the picture is a rainbow. So let's go back and find letter A. So letter A would be here, and we see that it's a rainbow. So that would be our visible waves. So we would go back to our reading, and this is the part that our eyes see. That's visible radiation. So you're going to do that with each one. So you're going to find letter B in Wavestown. So here's letter B. And what we want, it's a radio tower or TV rays. So going back to your description, you want to find that it's your radio waves. This is the same kind of energy that radio stations emit, and we could also see TVs, etc. So here you're going to write in your box radio waves, and you're going to do that for each one. So for your connection today, radio waves have long wavelengths, and you can see that here. You can look underneath to have a visual to see your wavelength from crest to crest, how long it is. So radio waves have long wavelengths of meters and low energy, while gamma rays have short wavelengths of only a fraction of a meter with high energy. Describe the span of the electromagnetic spectrum. So these are all your type of waves listed above, and then below you can see your wavelength. Quasars are extremely distant celestial bodies. Investigators using a spectral telescope determined that a certain quasar was emitting waves with a frequency of 1.41 times 10 to the ninth hertz. An electromagnetic spectrum is shown. So here you have your type of wave, and then below it is showing you the wavelength. So your STAR test question below reads, investigators were most likely using a telescope that detects what? So if we're looking at a certain quasar that's emitting 1.41 times 10 to the ninth hertz, you want to go down below here and see what wavelength would give you 10 to the ninth hertz, and look above, and then that quasar would be emitting a microwave. For your exit, you're going to click and drag the types of wave to the correct location and label the electromagnetic spectrum. You can use slide 9 as a reference. So here is your electromagnetic spectrum, and we're going to drag and drop the names of these rays below. So just from our introduction, you can see that your longest wavelengths are going to be your radio. So you can put that here, your radio waves. Over here, this would be part of your visible spectrum. And then if you click to your slide above here, you can use these to help you do your drag and drop.